Hey everyone, welcome to this explainer. Today, we're going to explore the fundamental states of matter that make up, well, absolutely everything around us. Whether you realize it or not, every single object you interact with, every drop of water you drink, and every breath of air you take follows a very strict set of hidden rules. And today, we're going to decode them. Seriously, just take a second and look around the room you're in right now. Ask yourself, why does the device you're watching this on feel hard and fixed in place? Why does water just flow so effortlessly when you pour it? And what about the air? It's brushing right against your face, but it's completely invisible and seemingly weightless. These substances are all made of matter, but they behave in drastically different ways. So here's how we're going to break this down in this explainer. First, the world we see. Then, introducing the particle theory. Third, inside the microscopic world. Fourth, explaining the physical rules. And finally, number 5, the vacuum exception.
All right, let's jump straight into section 1, the world we see.
Before scientists can figure out how something works on a tiny microscopic level, they first have to define the macroscopic rules. Let's break down the basics for the 3 main groups we use to sort matter. We'll start with solids. Solids are stubborn. They keep their shape, they keep their volume, and you absolutely cannot compress them. Then you've got liquids. They're a bit more flexible. They'll naturally take the shape of whatever container you pour them into, but just like solids, their overall volume stays exactly the same, and they can't be compressed either. And finally, there are gases. Gases kind of do whatever they want. They flow, they will completely fill up any closed container you put them in, and unlike the other two, gases are incredibly easy to compress. Moving on to section 2, introducing the particle theory. So we know what matter does, but we really need to uncover exactly why it behaves this way. What is the underlying mechanism? To answer that, we've got to think like scientists. When scientists observe something, like the fact that ice melts or a gas expands, they form a hypothesis, which is really just an educated suggestion for an explanation. Then they test it over and over again. Once that hypothesis has been rigorously tested and is widely accepted by the scientific community, it officially levels up into a scientific theory. And the absolute best theory we have to explain how matter behaves is called the particle theory. This universally accepted theory tells us that everything you see and touch is actually made of tiny, moving parts. Particles that are way, way too small to see with the naked eye. The reason a solid acts like a solid and a liquid acts like a liquid really just comes down to how these invisible building blocks are arranged. Let's zoom in for section 3, inside the microscopic world. I want you to imagine being in a packed stadium crowd where everyone is standing shoulder to shoulder in perfectly fixed rows. That is exactly what a solid is like. The particles are locked in a rigid pattern, they're held together super strongly and can only vibrate, just making tiny, rapid movements, but they stay exactly in place. Now think about a liquid. The particles are still touching, kind of like a crowd milling around on an open concert floor. They are held together much more weakly, which means they can actually slide past one another and swap places. That's exactly what allows a liquid to change shape and flow across the floor.
Now, gas particles are a completely different ballgame. They are independent wanderers. In their resting state, they don't even touch each other at all. Instead, they spread out entirely by themselves, moving freely and rapidly in all directions to fill up whatever empty space they're in. If a liquid is a crowd at a concert, gas particles are like a few lone hikers wandering independently through this massive empty wilderness. They are completely unbothered by one another.
Which brings us to section 4, explaining the physical rules.
So why do things hold their shape or flow? It all comes down to one hidden mechanic: the strength of the attractive forces holding the particles together. In a solid, those attractive forces are incredibly strong, locking everything into that fixed grid we just talked about. But in liquids and gases, those cohesive forces are either super weak or effectively non-existent.
Matter can only flow if its internal particles can physically move past one another. Because liquid particles have those weak attractive forces, they can slide past one another with total ease. This perfectly explains why you can pour a glass of water, but there's literally no way you can pour a block of wood. The wood's particles are locked tightly in place, while the water's particles are free to constantly tumble and slide over each other as gravity pulls them down. By contrast, because gas particles have basically zero attractive forces holding them together, they possess vast amounts of empty space between them, and that is why they are so easy to compress. Think about pushing down on a sealed syringe full of air. You aren't shrinking the particles themselves. You're simply forcing them to move closer together into that pre-existing empty space. You're just closing the distance between those lone hikers.
Let's wrap things up with Section 5, the vacuum exception.
Scientists love finding things that don't seem to fit the established rules. We just established that solids cannot be squashed because their particles are already tightly packed. But wait a minute. Think about your kitchen sponge, or even a soft marshmallow. They are definitely solids, yet you can easily squeeze them in your hand. So what's going on here? Do we just break our own rule? Actually, scratch that, the rule holds up perfectly. If we use the particle theory, we realize something pretty cool. When you squeeze a sponge, you aren't actually compressing the solid material at all. A sponge is incredibly porous. It's full of tiny, empty pockets, and those pockets are naturally filled with air, which is a gas. And as we just learned, gases have massive amounts of empty space and are super easy to compress. So when you squeeze that sponge, you're literally just squashing the gas trapped inside those pockets and forcing the air out. The actual solid particles of the sponge don't shrink one bit. I want to leave you with a pretty wild thought as we finish up. We've established that everything you can see, feel, and interact with is matter, built from these invisible, vibrating, or sliding particles. But what happens if you remove all of them? A space where there are absolutely no particles at all is called a vacuum. It contains literally nothing. So if everything that makes up our physical reality is defined by the presence of these particles, a true vacuum challenges our very understanding of what empty space even means. Are we ever really touching anything or just interacting with forces across empty space? Definitely something to chew on next time you pour a glass of water. Thanks so much for joining me for this explainer, and remember to keep questioning the world around you.